here in this presentation. This is my last day working as a research associate at the Chilean Center for Sustainable Urban Development. So it's a special day, and I hope you like this presentation and you have many questions at the end, because this we hope we can still improving this work in the future. So this presentation is entitled Understanding Regression in Urban Bus System, Evidence from Santiago, Chile. And the idea is to present an introduction, introduce the public transport system in Santiago and the bus fare collection system, and how this explain or produce variation in our system. And we also will present the framework to solve our research questions, the main results, conclusions, and further reasons. So firstly, I would like to talk a bit about our previous work of variation. The first paper was just published officially 2 days ago, so you can access in the link to download the paper for free. And then, based on this work, we wrote another paper, which we presented in the CEDEUS 14th conference, which was in Chile last year. And the idea was using the findings of the first paper and doing new applications to reduce variation using fare inspection, but in this case, fare inspector is this kind of fare inspectors that we study. They are not entitled to be fined for variation, but we found variation could still decrease and could be an prospective measure to reduce. In the first the MBTA in Boston, and in the second work we work with Susan Handy, which is a professor, full-time professor at University of California, Davis, and Juan Carlos Muñoz, the director of our BRT Center. So the transport structure, we have 10 different zones in the system. Each zone has a group of municipalities, which are geographical areas in Santiago, which are smaller than a zone in the system. There are 5 bus operators. Each bus operator operates buses in 1 or 2 zones in the system. We have feeder and trunk buses. Feeder just go around one zone in the system, but trunk buses could go around different zones in Transantiago. And there are actually 5 lines. The first system is integrated fare between metro and buses, and the payment is only by smartphone. So the first fare collection system, let's take a bus 3 doors, have a bus stop in the box in blue. So people are supposed to board by the front door and get off the bus by the back door, but this usually doesn't happen. But bus drivers are in charge of monitoring people in order to fulfill with this rule, and the smart card validator is nearby to the bus driver. Usually, all the smart card validators are at the front door, but sometimes there are two smart card validators. About the trend of variation is increasing over the time. At the beginning of Transantiago, it was in February 2027, and the first measurement of Regression was in May. It was 16%, and then it has a significant increase until the contracts with the bus operator and Transantiago changed, which gave more incentives for bus operator to handle Evasion, because the payment from the government was based also on the number of smart card validations in the system. Then the Evasion decreased significantly. Here we have October 2012, which was the sample which we used in the first paper of Evasion to calculate models and to obtain some conclusions. November 2013, we have the sample of observation we used to for the second study of Evasion. And the last measurement of Evasion was in this graph was in September and reached 23%, which is pretty high, and last statistic showed Evasion is still higher actually currently. So the study overview. Our main goal is to propose new methods to address Evasion as alternative to more dedicated fine enforcement. That's why we tried to estimate several advanced statistical models to find different explanatory variables that impact significantly of Evasion, rather than only analyzing the impact of enforcement, which is normally the approach used in the literature. We evaluate if ticket inspection is cost effective when evaders are not given a fine. This is a novel approach because literature generally study ticket inspection with fines. To determine where, when, and how much to invest in ticket inspection, we formulate a methodology of 4 steps. The first steps, I will explain the data collection process. We took advantage of existing databases collected by the government in the case of the first study, and then for the second study we used a database collected by a private bus operator in Transantiago, which allowed us to estimate regression models. And then, using the output of the regression models, we used an heuristic to allocate ticket inspectors optimally. And then in the final step, we performed a cost-benefit analysis in order to conclude if this strategy could be profitable, even if ticket inspectors are not entitled to fine fare evaders. About the data collection process. So here we have the bus drivers close nearby to the front doors of the bus. At each door of the bus is an anonymous observer is monitoring how many passengers is boarding the bus at a given bus stop where the bus stopped. How many boardings, how many exitings, as well as other variables that we will explain further. And this group of anonymous observers started at the terminal station of a given bus route, and then they collect observation until the bus arrive at the next terminal station. So this guaranteed to have observation in different bus stops of that bus route, and in different periods of the day, and in both ways of the bus route. And it should be noted, boarding can be registered at any door, because normally people don't follow the rule established for boarding and alighting, as well as people can exit. In the observation, you can see people are exiting at any door. The data available. Firstly, in which door was collected the observation, the month, day, hour, and minute in which the observation was collected,
the number of failure at that door at a given bus stop, number of passenger boardings and exitings, if there are ticket inspection monitoring passenger at the bus stop, which was measured, and the stop location, which can be inferred using the GIS code provided by the private operator, and the bus route and the bus size. But it should be noted the information not collected on individual characteristics, so we can't include in the model variables as the gender of ferry evaders, the age, as well as other socioeconomic variables, which would be very interesting to analyze this phenomenon. But it's a limitation of this study, and we are going. Our objective was to take advantage of all the explanatory power can be provided by the database for estimate the regression models. About the data, we have 107,000 observations, 115,000 passenger boardings, and 32,000 for evaders, which are is a very large database to analyze this phenomenon. 62 bus routes operated by one private bus company in the system, which they provide the database for this study. The level of aggregate observation at the level of at each door and bus stop where a bus stopped. We use a new level of aggregation we watch bus by bus. So please don't feel confused about this difference, because all the further analysis they're gonna be by bus stops and not by each door of the bus. The estimation sample to estimate the regression model, we use only data collected from November 2013 from these private operators, and then to apply the heuristic in step 3, we used information collected from December 2013. About the data cleaning process, we didn't include in the analysis observation with missing data and other basic inconsistencies, such as the number of ferry evaders are greater than the number of boardings that were measured at a given door. We didn't include also observation collected in off-board payment stations because the anonymous observers are sitting down into the bus, so then they can't really monitor if passengers pay the bus fare before boarding the bus, because that's the way how off-board payment stations work. So they are instructed to register no fare evasion at that bus stop, but that's clearly not clearly an error, have some error this observation. So we decided to not include those observations in our regression models. And in order to estimate the model, we didn't include observations when nobody boarded the bus, because they don't provide additional information in the model. If nobody boarded the bus, then you expect no count of variations. And we create 3 variables: one for to control for the effect of bus occupancy, the socioeconomic level, and the theoretical headway. Some summary statistics. In the first column, we have the different variables were available in the database. And the second column, the minimum, then the maximum of the value, the mean, standard deviation, and coefficient of variation. So I will highlight only some values of this table. So firstly, we can observe variation. The coefficient of variation is very high. The coefficient of variation is calculated as the ratio between the standard deviation and the mean of this variable. So that's saying basically variation changed a lot. In the count of variation changed a lot depending on what what observation is being analyzed, and this could have this could produce many problems if we estimate the traditional regression models such as linear regression, and we decided to try other model specifications which can account for this effect. Of course, this is descriptive. These are descriptive statistics, so we can't ensure necessarily there are problems with over dispersion in this database. But this is this could indicate there is a problem with then we perform some of the monthly household income. Once because we know the municipality, then we assign to that bus stop a certain level of monthly household income using socioeconomic some data collected from the government to estimate the monthly household income depending on the comuna or Santiago, and we add these variables in the database. We can observe the minimum the minimum monthly household income is $750. The maximum is 6,000, and the mean is pretty low. So we have a sample taken in very poor income areas in Santiago. And then the level of occupancy, which we calculate as the number of passengers at the bus at the moment when the observation was collected, divided by the bus size. The bus size is defined previously by the private, but the manufacturers of buses, and account for the number of seats of the bus, but also the passenger that can be at the platform. So here we have more summary statistics. Category. Here we can observe the variables and the level of each variable. In the case of ticket inspector monitoring the bus stop at the for the observation is being if there are, then a fare evasion rate is decreased significantly compared when there are no ticket inspector, which is 30% of fare evasion. In intermodal station is observed fare evasion decrease significantly too, and here we have we define 4 socioeconomic levels depending on the monthly household income of the comuna linked to the observation collected, and in the low income areas, low income municipalities, fare evasion is significantly higher than the other ones. So about the regression model estimation, we tried 3 families of 3 types of regression model. For multiple linear regression model, which is the traditional approach, using the rate of fare evasion as the logarithm of the fare evasion rate as the dependent variable. The binomial regression model, which basically is trying to explain the number of trials, the number of count of fare evasion, but regarding the number of controlling for the number of boardings, which are basically the trials of the distribution, and the number of successes correspond to the number of fare evaders that are counted on that observation. And then 2 different count regression model, Poisson model and negative binomial, to account for the over dispersion we found in the data. The dependent variable for the binomial count regression model was the amount of evasion at a bus stop and given time of the day, and the explanatory variable were related with the bus operation, the number of boardings, number of alightings at the bus stop, number of doors, and the bus occupancy. Temporal variables, which we define based on the statistical significance of the time using different time groups of time of the day. We divide, we add some explanatory variable I will explain further. And then some variables related with the geographical area, the level of income of the comuna, the municipality where the observation was collected, if there is a metro station nearby to the bus to that bus stop, and or an intermodal station, some variable related to the ticket inspection, and the variable headway in this case, and the type of bus route, which are feeder or trans, were not significant in this case. So here we have a table with the 4 regression model we estimated. Here we have the variables we include in all models, and first the variable related with the bus operation. We have here the, I will explain the number of, why we use a logarithms. We control for the number of exitings at the given bus stop where the bus stopped, which was the level of aggregation used for estimating all these models, the number of doors of the bus, the bus occupancy, which is the ratio between the number of passengers aboard the bus and the capacity of the bus size. Temporal variable we define as the base dummy, the weekend, and so then we define two other categories which were morning weekday or afternoon weekday. For the geographical area, we add if it's the bus stop where the observation was collected was nearby to a metro station or another dummy if the bus stop is nearby to an intermodal station. We control for the level of income of the comuna. In this case, based on the statistical significance obtained for the parameters, we find only 3 different income levels. The first level was lift up the reference group of the dummy variables. So income 2 represent a medium monthly household income, and the income 3 represent a high monthly household income in Santiago. Then some variables to control for the effect of ticket inspection. First, just a dummy variable if there are ticket inspector monitoring at the bus stop, and then an interaction between inspectors, if there are ticket inspector, but also the observation was collected in a high income area in Santiago. This is interesting because this inspector cannot ferry evaders. So if you have if there are hard evaders, which are people are going to evade the ticket even if someone is trying to stop them, then just ticket inspectors are not going to be very effective. So we would expect this could be especially, we suppose this was especially true in low income areas where you can where passengers are not able, most of passengers are not able to pay the bus fare, so these ticket inspectors are not going to be so effective. So we will expect if inspectors are located in high income area, they are going to have a greater impact in fare evasion. So that's why here we expect a negative sign. This is saying if there are ticket inspector at the bus stop, fare evasion is going to decrease in this magnitude. But if in addition the inspector is allocated in a high income area, fare evasion is going to decrease even more. The same with the weekend. In the weekend, we find fare evasion is going to increase even more. So about this variable in the binomial model, for the definition of the binomial model, the number of trial of the process has to be defined. In this case, when the number of trial would be the number of boarding, so it's not necessary when the model is estimated, the number of boarding is added as the number of trial, so it's not necessary control for that. But if the data is very over dispersed, and you expect this model is not going to perform well, And then some literature suggests to estimate count regression models. In this case, we estimate a Poisson, and to control for the number of boardings, because naturally you expect evasion increase as the number of boarding increase. It's added an offset variable or exposure variable, which is a variable which has a logarithmic form, but the coefficient of this variable is fixed to 1. This allows to control for the effect that if fair evasion increase, the number of fair evasion increase naturally as the number of boarding increase. For the form of the negative binomial regression model, the offset is added again as a logarithmic variable with the parameter fixed to 1. But then we estimate again a negative binomial regression model, but not fixing the coefficient in 1. So not using an offset, but capturing the fact that number of boarding is naturally increased fair evasion. And in this case, the coefficient is slightly higher than 1, which is representing that fair evasion rate increase as the number of boarding increase. And this could be explained basically for the anonymity of passengers. If there are, if passengers are boarding the buses in bigger groups, then you expect that anonymity could impact significantly in the fair evasion rates. And here we have two different statistics for the goodness of fit of each model. The log likelihood can't be compared between the binomial model and the other model because it's not a model nested in the Poisson model and the negative regression model, but the Acknowledgement information criteria, the AIC, it allows to compare different models if the sample for the estimation is. In this case, we can see a significant decrease in the AIC for the Poisson model comparing to the binomial model. The difference is almost 2,000, and this test normally suggests that a model performs better where the difference is greater than 10. So clearly, the Poisson model performs better than the binomial. And here, the negative binomial regression model performed better than the Poisson. The difference is again 2,000. And then the model using not using an offset but using a exposure variable performed even better. But the main negative binomial regression model and the other model. So we can confirm our approach is the correct approach. So here we have some equations. Basically, this model can be the negative binomial regression model as well as the Poisson models can be estimated by a maximum likelihood estimation, and they are generally linear models. Or also for Bayesian method, we use the maximum likelihood estimation in this case. And for this, we define a probability distribution for the counts, in this case of fair evasion, for a given observation. And then a link function is defined to relate the expected value of the PDF, the probability density distribution of counts, to a set of predicts X and parameter beta. And in this case, it's added alpha, which is it's called heterogeneity parameter, in order to control the over-dispersion, which is not captured in the Poisson model. So this parameter is very important and allow us to test if there were over-dispersion in the data, and we finally found that in our data. So if we observe the expected value of the distribution has a logarithmic form, so we can estimate percentage factors which represent what is the percentage change in the expected value of the distribution, which in this case is fair evasion. If there is a unit change in the value of an independent variable, in this case could be ticket inspection. So, and this variable keep this value keeps constant regardless the value of the explanatory variable. So then, using the output of the regression model and estimated parameter of the related to the ticket inspector variables, we calculate the percentage factor of variation if there is ticket inspector allocated at the bus. So this output was used for the next step in the heuristic. In the third step, firstly we construct a matrix with the slot in which ticket inspector can be allocated. Each slot is given by a period of the day, a given a given bus service, a given bus service, and a given bus stops. So ticket inspector can be allocated in many slots, which are given for the characteristics I discussed before. I'm going to show an example in the next slide. Then we calculate the minimum number of ticket inspector to satisfy the demand of passenger at each slot. If there are a high flow of passengers arriving at the bus stop, naturally you would need more ticket inspector to monitor effectively all the passengers arriving at that bus stop. So we define also a capacity, which is the number of passengers which each ticket inspector is able to monitor at a bus stop. Then we calculate the number of evaders that each inspector reduces per hour, given by the percentage factor we obtain from the regression models, and also using the variation rates at that bus stop, the current variation rates at that bus stop. And then when we allocate the ticket inspector based on the level of productivity of each slot and the time horizon is being analyzed. The process is performed iteratively until no more money is available. So let's take this table. We will have five different options to allocate ticket inspector, and we have a certain amount of money to invest in this strategy. So each bus slot will be linked to a bus route, a given bus stop, time period of the day, and the slot is going to have a length. So we will think if we're analyzing morning peak hour, so the morning peak hour period is 2 hours, so the maximum number of hours that inspector can be allocated in this slot are 2 hours. So that is our constraint of the model. Then the rate of arrival, which we estimate using the data collected from December 2013. Then we define a capacity of inspector, mu. We calculate then based on the mu and the rate of arrival, what is the number of inspector necessary to satisfy the demand of passengers that arriving at that bus stop, which is the minimum number of inspector. Then we calculate, or we assume an evasion rate based on the data collected from December 2013. The percentage change factor are obtained from the regression models, and they are going to change depending on the level of is being implemented and the time period, because we saw in the regression models the parameters are different depending on these two variables. And finally, we calculate the productivity per inspector as the product between the percentage change factor, what is the percentage change in variation if inspectors are located at that bus stop, and weighted by the current variation rate, and waiting for the value of reducing variation, which can be assumed as the current bus fare in the system. And finally, depending on the productivity of each slot, we allocate inspectors. So here we have a graph in which we calculate the marginal productivity of inspector. In the x-axis, we have the total time of inspection, which we basically, if you have a given budget to invest in this strategy, you can calculate directly how many hours of inspection is equivalent to this budget, and then this heuristic allocate optimally or smartly, I don't know what is the word, but inspector on this in these different slots or possibilities. So the black curve represent the marginal productivity of inspector for the lowest income level, and then the red curve represent the marginal productivity for the medium income level, and then the blue curve represent the marginal productivity for the high income level. We can observe the productivity is higher in the low income area, which could be explained because even though ticket inspector reviews more variation in low income areas than high income areas, we saw that in the table when we presented the result of the regression models. If the inspector are in low income area, then the reduction of variation is going to be higher, but variation rates on low income areas are higher. So it's more, ticket inspector are going to find more validators, and then they are going to reduce in absolute terms more variation, and they're going to be more productive. The problem in high income areas, which is the group in curve, effective. If a ticket inspector or validator are, we would say, soft evaders, then ticket inspector are more have a greater impact of validator, but the variation rates are lower. So ticket inspector are basically monitoring passengers that are not evading, and they are going to reduce just a small proportion of variation. So that's why that explains the difference in productivity. The cost-benefit evaluation. We have three curves. The red curve represents the average revenue. The black curve represents the marginal revenue, and the blue curve represents the marginal cost. The marginal cost was assumed as the marginal cost of 1 hour of inspection was assumed at close to $4 per hour. And it was assumed constant, so that's why it's just a straight line. And the area under this line is going to represent the cost of ticket inspection using a given amount of total time of inspection, right? Then the marginal revenue curve is decreasing along the total of inspection increases. This is because at the beginning, the heuristic allocate the time of ticket inspector at the most productive bus stop, where the variation rates are higher and where the impact of the ticket inspector is higher. So then the profits are going to be higher. But then the heuristic start to allocate the ticket inspector in bus stops that are not very productive, and the productivity, the marginal revenues, which are given as the product between the marginal productivity and the bus fare, naturally decreases. Average revenue, which if the marginal revenue decrease, then the average revenue is expected to decrease also. And using the microeconomic theory, the intersection between the marginal cost and the marginal revenue is going to represent the point where the most profit can be obtained. So this area basically represents the net benefits of this strategy, which in this case are positive. So this is we think this is a very simple way to analyze the result of our heuristics, and we can see results are consistent with the microeconomic theory and even with our expectations. Of course, there are some points in which the benefits are not going to be optimal, but we're paying attention of this optimal point. So, as a summary of all the results obtained in this study, about the regression model assumption and goodness of fit, all parameters obtained in the regression model were statistically significant and their signs were consistent with our expectation, even though the negative binomial regression model performed better than, significantly better than the other models. All the models present the parameter with sign and with signs statistically significant consistent, which show is these variables are impacting Evasion consistently regarding what the model are we using. This was a I would like to clarify this because this was a long discussion we had in a Chilean conference last September about what approach would be better, or using a model of proportion, such as the binomial regression model, or using counter regression model. But we can demonstrate here the counter regression models is the best approach. So after trying different specifications, negative regression model is better. And if you want to know more details about the statistical validation of this model, the test for over dispersion, you can see the paper we presented in the TEDPO conference. You can mainly I can see. So another important result is Evasion rate increase as increase the number of boardings, number of alightings, the number of doors, and the bus occupancy. We have some explanation for this result. We can you can find in the paper, or if you want clarification, we can discuss it during the questions. But a Evasion rate increase has decreased the socioeconomic level of the municipality. We discussed already this during the presentation. If the bus stop is not located nearby to a metro station or intermodal station, and we think this could be capturing the fact that close to metro station, the proportion of passengers that are using buses were using the metro before. So if they pay buses after using the metro station, they don't have to pay more money or just a small amount of money for using the because we have an integrated system. So there are no many because the cost, the saving for the passenger are not so high. In addition, close to metro station, there are places to increase the balance of the to put money in the smart card. So then Evasion could be reduced by the effect of these places. And finally, the Evasion and the afternoon. This is this effect or this result is obtained by capturing all the effect of the other variables. So there are some aspect, some behavior, particular behavior of the people during the weekend and during the afternoon that produce more Evasion that are not explained by the past level of occupancy during the afternoon or the geographical area and so on. The impact of ticket inspector depends on the sale of the municipality and the period of the day. The highest productivity is in low-income municipalities and during the weekdays, but the highest effectiveness in high-income is in high-income municipalities and during the weekend. When we talk about effectiveness, we're saying basically we're talking about the productivity. We're saying even if Evasion is proportionally reduced significantly, if Evasion rates are low, then ticket inspectors are not going to generate a lot of profit. But they could be very effective because they decrease significantly the proportion of evaders of high income areas, right? And about policy implication, we conclude with this result. Fair evasion can be tackled without necessarily more dedicated fine enforcement. Our result showed that ticket inspection was cost effective for a large range of investment level and a short time horizon. Conclusions, and this was one of the motivation of this seminar. Fair evasion levels are the product of a combination of factors including the level of service, such as the bus occupancy, the characteristics of the geographical area where the buses are located. We capture this effect partially using the monthly household income of the municipality where the buses were located, and the level of enforcement, which is the variable that is usually studied in the literature to explain fair evasion. But we added other factors that were significant to explain it. The use of regression models and the microeconomic analysis provided a powerful and simple tool to increase the cost effectiveness of ticket inspectors. And this study contributed with new evidence that indicates that inspection strategy can be cost effective even when fair evaders are not given a fine. And we expect in further research we can analyze other strategies that doesn't involve necessarily fine fair evader, but that could be effective to reduce it. That's why the first point of the further research is to formulate a cost-benefit model to help authorities determine the budget distribution among a set of strategies for dealing with fair evasion, such as increased bus frequency. Why increase bus? If bus frequency are higher, then bus occupancy levels are going to decrease, and then this would decrease fair evasion as we observed in the result obtained in the regression models. Increase the bus size, again, reduce the bus occupancy. Implement or payment station has the same effect. And increase fair inspection that we show in this model is very effective. Could be very effective to decrease fair evasion, even if fair evaders are not given a fine. And second, formulation of a model to predict fair evasion using smart data. We are currently working on that with a group here in PUC, and this will allow, for example, to predict fair evasion rate in each inspection log without assuming fair evasion rates known previously, as we did for this study. In addition, we will calculate the changes of fair evasion due to improvement in the level of service. For example, what is the reduction of fair evasion if we decrease the level of occupancy of buses in Santiago? And we are going to use this model using as input the smart card data, and we are going to calculate changes in fair evasion and each observation, and then we can calculate in an aggregated level in the city what would be the change on fair evasion. That would be pretty interesting, and we are working on that with input. In addition, because of especially when fair evasion is so high, the estimation of bus load profiles is very bad, right? So using this method, we also developed some methodology to correct I would say increase the value of the bus load profile, accounting for the effect of fair evasion. Actually, bus load profiles are underestimated because they are estimated using smart card data, and they are not accounting for fair evasion properly, at least. My acknowledgement: this research was benefited from the support of the Center for Sustainable Urban Development, the Bus Rapid Center of Excellence, the Enforcement Commission of the Chilean Transport Ministry, who provided the dataset for the model we estimated in the first paper, and SUBU Chile, who provided the dataset for the second paper. Thank you. Thank you, everyone.
Hi everyone, we have a few minutes if you want to ask some questions in the question side, the launcher of the webinar. If you want to ask, I want to thank Pablo. He's the last day before he goes, so I think it's a great experience to present to other people what he knows and to give this insight of innovation so we can work and to download how many evaders we have.
So if someone have any question or comments, please let us know, and we're going to try to find a good answer. Or if if you're not satisfied with that answer, we can talk later by email.
Well, in that case, if people have questions, you can send me an email with your question and I can tell Pablo to respond to. Thank you, everyone. This presentation and video will be uploaded on the BOH Center of Excellence website as usual. So have a nice day. We hope this year we haven't seen this since last year, so very good one, and hope to see you in the next webinar. Will be in March probably. We are going to send you the invitation when we have more information about that. Thank you, everyone, and